A digital twin is a virtual representation of a real-world entity or process. It is composed of the following three elements: a physical entity in real space, the digital twin in software form, and data that links the first two elements together. A digital twin functions as a proxy for the current state of the thing it represents. It also is unique to the thing represented, not simply generic to the category. Moreover, the digital twins of two seemingly identical products will not usually be identical. While many digital twins have a 2D or 3D computer-aided design, CAD image associated with them, visual representation is not a prerequisite. The digital representation, or digital model, could consist of a database, a set of equations or a spreadsheet. The data link, often but not necessarily two-way, is what differentiates digital twins from similar concepts. This link makes it possible for users to investigate the state of the object or process by querying the data, and for actions communicated through the digital twin to take effect in its physical counterpart. The Digital Twin Consortium, an industry association working to build the market and recommend standards, adds an important phrase to the basic definition: synchronized at a specified frequency and fidelity. These qualifiers refer to three key aspects of the technology. Synchronization is about making sure the digital twin and the represented entity mirror each other as closely as possible. The frequency, or speed, at which data gets updated in a digital twin can vary enormously, from seconds to weeks to on demand, depending on the purpose. Fidelity is the degree of precision and accuracy of the virtual representation and the synchronization mechanism. Digital twins are created using the same CAD and modeling software that designers and engineers use in the early stages of product development. The difference with a digital twin is that the model is retained and updated for later stages of the product's life cycle, such as inspection and maintenance, and often managed in Product Lifecycle Management (PLM) software. The physical connections between the entity and its twin are most often IoT sensors, and a mature IoT implementation is often a prerequisite for digital twins. It's also been said that IoT equally needs digital twins because they bring structure, analytics and usability to IoT data that is otherwise disorganized and hard to interpret. The symbiotic nature of the relationship was raised in a 2019 Gartner study that found broad adoption of digital twins among IoT implementers. Finally, analytics, often bolstered by AI and machine learning, is essential in processing and analyzing digital twin data. Types of digital twins: several ways of categorizing digital twins exist, but the following four categories, organized in a hierarchy, are by far the most common. Component twins, also referred to as part twins. The most basic level, it's not for simple parts like screws but for things like mechanical subassemblies. Asset twins, product, two or more components whose interaction is represented in the digital twin. System twins, unit, assets assembled into a complete, functioning unit. Process twins, systems working together to serve a larger goal. Because they're virtual, digital twins can reduce the cost and risk of having to work on the physical things they represent. Further benefits includes improved operational efficiency from having more timely data and faster, more effective production, more effective and less expensive R&D from replacing physical prototypes, which can be expensive and hard to modify, with virtual prototypes that are more flexible and produce more data, longer uptime for equipment because maintenance issues can be investigated in a single digital twin instead of having to shut down all the equipment to isolate a problem. Improved product end-of-life processes, such as refurbishment and recycling, thanks to more accurate information about the age and contents of a product. Organizations looking to develop digital twins face other daunting hurdles. 6 of the biggest digital twin challenges are data management, data security, IoT development, system integration, supplier collaboration and complexity. The industries are seeing the most activity in planning or deploying digital twins are manufacturing, utilities and energy, healthcare, urban planning and construction, automotive and retail and e-commerce. In the near term, developers are likely to expand the use of digital twins to a broader range of entities, from body parts to people, from smart cities to global supply chains. As the price of digital twin technology comes down, companies will no longer limit its use to their most expensive, mission-critical equipment. The continued growth of digital twin development options, IoT infrastructure and related concepts like the metaverse should help popularize digital twins and make them easier to deploy. Thanks for watching Techaks. All about tech. Please like and subscribe for more tech related videos.